Smadja from the University of Nantes, and he will be speaking on From Diophantus to Philology, Contextualizing C. G. Jacobi's late engagement with Diophantus text. Smadja.
So first, thank you. Oops. I would like to thank very much the organizers of this event, this conference. Thank you for the invitation, and also it's an honor, a pleasure, and a daunting honor to speak after Norbert. As a matter of fact, as you will see, what I will present now is very much indebted to part of his work. As a matter of fact, I will start taking my cue from some of his papers. So, from Diophantine analysis to philology, what's the sequence I propose to go through? This one. Why? First, conflicting interpretation. In 1835, Carl Gustav Jacob Jacobi published a short note in which, in reference to some of Euler's posthumous memoirs, published a few years earlier, he highlighted the close connection between Eulerian Diophantine analysis on the one hand and elliptic and abelian integrals, which he contributed to develop in no small measure, on the other hand. Much later, this note played, as you know, a pivotal role in the shaping of a much controverted reading of Diophantus Arithmetica. It was argued that Jacobi's note could be read both ways, whether as prefigurative modern standard algebraic geometry, or as providing presumably convenient tools for making sense of Diophantus' ancient methods. And from the 1970s onward, a well-known historiographical debate unfolded in which conflicting interpretations were being confronted. So let's first start by a quick survey, a quick overview of this debate, this kind of historical debate like the discipline is accustomed to. The whole debate revolved, as you know, around the use of the language, concepts, and methods of modern algebraic geometry for reading Diophantus text, starting with such bold statements as the one by Izabela Bashmakova, claiming that considerations of algebraic geometry were already there in the text, although within the framework of pure algebra and number theory. With, a few years later, this caution put forward by André Weil that one should not forget that geometrical language is precisely absent from the text, but still. Later, Rojdi Rashed, historian of Arabic sciences, published his translation and commentary of the Arabic books. Here it is the fourth, but there is the others too, with an introduction providing some tools from modern algebraic geometry, in particular the so-called chord method for curves of genus 1. So, taking up this kind of approach. Then, in a couple of papers, Norbert made very crucial distinctions, as you know, putting forward first that interpreting Diophantus' substitution in the light of modern methods is one thing, surreptitiously identifying the former with the latter is quite another. And it is not uncommon that historians of mathematics fall into this trap, it seems. And in another paper on Diophantus' text and its history, Norbert proposes to go, he selects three well-chosen problems from Diophantus' texts, offers a detailed analysis of these problems to show that Bashmakova's interpretation doesn't hold water. So, later, Rojdi Rashed and Christian Houzel published their books, they maintained the fruitfulness of their approach, but as you see, adding quotation marks to those labels like the chord method or the tangent method. So in their view, in the introduction, they explain that modern methods offer an interpretive model, a heuristic tool allowing to identify Diophantus' method and to shed light on the way they are organized into a consistent whole. Although obviously absent from the Greek text, these methods can be read between the lines. The French expression is comme en filigrane. So the whole point is about this, see. Before later, and actually very recently, Jean Christianidis and Jeffrey Oakes published a complete translation and commentary of all the books, not only the Greek ones, but also the Arabic ones, within a completely different framework, because they make a case that Diophantus' methods for solving arithmetical problems are envisaged within the framework of what they call pre-modern algebra, a pre-Vietnam algebra practiced in Arabic, Latin, and European vernaculars before the 17th century shift in perspective. Okay, all this is well known. So, Jacobi's 1835 note hovers in the background of all this historiographical debate ever since Izabela Bashmakova made it pivotal in her own interpretation of Diophantus' methods. But another perspective, though, prompts new questions, putting a premium on actors' categories. So the question I would like to address today in this talk is precisely to understand better the relationship, how Jacobi himself viewed the relationship between his earlier work and his later engagement with Diophantus' texts. So what was Jacobi's purpose in 1835? And chiefly, how would he later conceive of the relationship between this earlier mathematical endeavor and his later philological work on Diophantus' text in the course of the 40s. So here you have, this is part of Izabela Bashmakova's book, where she explicitly refers and adopts the notation of Jacobi. So, and this is, as you will see, connected in some way to the work that was presented by Norbert in the previous talk, that is the current work that was done by the group on the Briel-Noether translation, and you will see how. So let's go back to Jacobi on Euler's legacy. So let's go back to into what Jacobi was pursuing in this note. This shorter text, it's only a few pages, opened with the observation that the very formulas which Euler used to solve this Diophantine equation are exactly the same as those occurring in Euler's work on the multiplication of the elliptic integral, the corresponding elliptic integral. And he also claimed that this memorable agreement probably did not escape Euler. So Jacobi's words are consensus ille memorabilis. So this is very well known, and this question was taken up by André Weil in his book on number theory. André Weil wondered whether one could find any textual evidence that Euler saw the connection himself. And his conclusion is, we have no way of telling. Actually, Euler gives no hint that he perceived such facts. So, whatever the case may be, Jacobi's purpose then was to pursue Euler's track way further and to generalize the connection between Diophantine analysis and elliptic and abelian functions. And here I would like to highlight this part at the end of the paper. So it's a paper written in Latin, and Jacobi says, if you ask, however, which increases from the abelian theorem that wonderful amplification of the Eulerian theorem, redound to the Diophantine art, you easily deduce from that theorem, namely Abel's theorem, properly examined, this proposition. So the whole point then was to extend the connection between Diophantine analysis and elliptic functions through switching from Euler's addition theorem to Abel's theorem, holding for a much broader class of equations. So, in the interest of time, I won't delve into Euler here, but Euler already explicitly aimed at extending Diophantine analysis beyond the domain of what it took to be Diophantus methods. So there are a certain number of papers where he reflects on the very meaning of this term Diophantea analysis, and it's very much clear that he tries to make clear in what way the path that he tries to open goes beyond the ancient methods. But with Jacobi's extension to Abel's theorem, the gap even increased. So let's go back a little. Let's try to contextualize it a little. And with a focus on a manuscript copy by one of Jacobi's students, Johann Georg Rosenheim, of a lecture course on elliptic functions of the winter semester 1835-1836. That is exactly the same moment when he wrote this note. And this manuscript copy bears witness to rapidly shifting mathematical landscape. As is well known, for the first time in this period, Jacobi investigated in depth the connection between the elliptic integrals of the three kinds and the theta function, deriving the properties of the former from those of the latter, from periodicity to addition theorems, and from there proceeding to Abel's theorem. But he asserted the novelty of his result in no uncertain terms. So if we pick up, we select these two quotes, which are interesting. Neither Fourier nor Abel had an insight into the connection between this function, the theta function, and elliptic integrals. And the second is more puzzling. Going back to the Legendre's way to deal with elliptic integrals, he wrote, although Legendre started from the general determination of the three types of integrals, he could not break up with the physiocratic principle of his time. He therefore considered it his main tendency to determine the numerical values of the integral. So the physiocratic principle of his time, what could it be about? It's really interesting to see. Look at this. Here on the left, you recognize Legendre Damier analytique. So Legendre was at a certain stage of the development of his theory of elliptic integrals, worked with two moduli. Okay, so he could organize the transformations into a damier checkerboard. And on the right here, you have the tableau économique by François Quesnay. And in both cases, you see that you have the synoptic presentation, and the possibility to follow the track of the way a real quantity transforms. So Jacobi's thought-provoking witticism probably referred jointly to two related aspects of the physiocratic doctrine of the 18th century, namely François Quesnay's well-known maxim about land being the sole source of wealth, real value, and the synoptic principle governing the so-called tableau économique used by the physiocrats. So both Quesnay, tableau économique, and Legend's damier analytique partake of this tabular form characteristic of the period. Both also allowed to keep track of the real quantity through transformations. And this tabular form characteristic of the period, when reading this, we cannot help thinking of what Michel Foucault wrote in the Les mots et les choses about this being precisely the characteristic form of thinking of the 18th century and the end of the âge classique. So here we see that there's really something very interesting in Jacobi's perceptiveness of the fact that he was breaking up with a state of the theory that, in his view, belonged to the past, the physiocratic principle of bygone age. But the quip stressed also that, in contrast to Legendre, Jacobi had known how to break up with these ancient forms. So his 1835 note on Diophantine analysis and elliptic function was meant as breaking new ground in mathematics at its peak, rather than shedding light on its remote past. So you see, the question that comes to one's mind is, then what about the past? When he turned at some point in his career to Diophantus' text, what was his take on this text? What was his view of the relationship between modern methods he was contributing to develop, to amplify, and ancient methods? So the next step is the connection between the discussion between Humboldt and Jacobi in their correspondence. While preparing the second volume of his great opus, Cosmos, Alexander von Humboldt submitted to Jacobi a series of queries on ancient and modern mathematics. Among those queries, dating from the late 1846, he wrote, Humboldt, "What I beg of you is a few pages capturing something characteristic for every one of the great powers of antiquity." So it's in this oceanic style of Humboldt in Cosmos, that is to try to figure out the relationship between what he calls the great powers of antiquity, that is seeing to make a consistent picture of what was brought by the Greeks in mathematics, of course, but also the Indians, the Arabs, etc. So trying to figure out how all these things would connect with one another, what were the influences, etc. And a few months later, he wrote, "My next requests are then for the Roman Empire," that is the corresponding section in Cosmos, "Diophantus and Pappus for the Arabs, look at Mohammed bin Musa, which I sent you, in which I mentioned Brahmagupta and Bhaskara." So here, Humboldt sent Jacobi some of the relevant literature on the question and asked for his expertise. More specifically, Humboldt required Jacobi's guidance to assess and organize into a consistent view the wealth of often conflicting ideas on history of mathematics, resulting from new scholarship, increasingly taking into account non-Western mathematical sources. But mainly for what is at stake today, the book, the translation by Henry Thomas Colebrooke of some Sanskrit sources, namely Brahmagupta and Bhaskara, first, then Charles' Aperçu historique des méthodes en géométrie, Libri, Guillaume Libri, Histoire des mathématiques en Italie, and Nesson, Die Algebra der Griechen. So, in this debate, that was the current debate then, and what is interesting is to understand in what way Jacobi took hold of these debates and how these debates filtered in his approach to Diophantus' text, given that he had this broader view from his earlier mathematical work. So what I would like to understand is precisely how Jacobi himself approached these thorny issues. So among the issues on which Humboldt solicited Jacobi's expertise were questions of origin, what is algebra and who invented it, Diophantus or the Indians, questions of categorization, how to characterize the main features of the different mathematical traditions, questions of nomenclature, what is exactly the difference between the so-called analysis and algebra. So, in turn, questions of origin. What is algebra and who invented it? Charles, in a nutshell, Charles held the two sources theory, considering that Diophantus and the Indians were the joint inventors of algebra. Libri, in contrast, claimed that the Indians were to be the only ones deserving to be credited with the invention of algebra proper. Both Libri and Charles were greatly indebted to the work of the British Indologists on Sanskrit mathematical sources, that is, namely Colebrooke and Strachey, who first put on the agenda the question of the comparison between Diophantus and Indian algebra. Questions of categorization, how to characterize the main features of these different mathematical traditions. Nesselman here plays the central role. Nesselman, Georg Heinrich Ferdinand Nesselman, studied mathematics under Jacobi in Königsberg and Sanskrit with August Wilhelm Schlegel. And he was very much acquainted with Colebrooke's work on ancient Sanskrit mathematical sources. But precisely on the base of this is very close knowledge of this new scholarship, he turned to the Greeks. And he wrote this book, Algebra der Griechen, a book that is dedicated to Jacobi, but focused on Diophantus, so as to characterize the way in which Diophantus' method could be characterized as Greek algebra. Question, more generally, as you know, in this book, Nesselman distinguished three different steps or stages, Stufe, in algebra: rhetorical algebra, syncopated algebra, and symbolic algebra, and in a certain way put the extant texts of the tradition into these categories. So according to Nesselman, Diophantus' methods would belong to the middle stages, whereas Hindu works was to be classified as symbolic algebra. And Humboldt wanted to benefit from Jacobi's thoughts on this. He pressed Jacobi to give his view on this current debate. Questions of nomenclature now among the Vexata questiones. What is exactly the difference between the so-called analysis and algebra? So Nesselman had a very, he was not the first. There was someone, Ludwig Hiedeler, who came up with the same idea earlier, but it's the first time that Nesselman make a consistent case based on really an assessment of the sources. He held the view that Greek algebra idiosyncratically originated from geometrical analysis. So he wanted to make a point that there was a brand of algebra that was rooted into Greek mathematics. So algebra, in his view, this is here Nesselman writing. Algebra is nothing else than the method of geometrical analysis applied to calculus. So Humboldt asks Jacobi about whether these denominations of algebra analysis should retain the same meaning in modern mathematics as in ancient mathematics. And Jacobi would answer, but in a different way than the way, what Humboldt expected. So here, let us keep in mind Humboldt's question for what comes next. So there is a couple of testimonies to Jacobi's commitment in the period. First, a letter he wrote to his brother Moritz at the end of December 1846, just when I wanted to put the last hand to that, namely the Memoirs on Analytical Mechanics, a series of questions on Greek mathematics was sent to me by Humboldt. Now it is my misfortune that all this make me plunge into a notion of investigations, so that without answering Humboldt's question, I spent 2 months only on these studies. And here, another testimony. A young philologist, Johannes Horkel, wrote to the classicist Karl Leers, a colleague of Jacobi's at the Albertina, I owe Jacobi many interesting hours. He is immersed in Diophantus and makes conjectures like an old Olander. He is completely surrounded by Greek mathematics, and I have learned a lot with him. So in response to Humboldt's question, Jacobi jotted down some reflections on Greek mathematics, part of which were inserted in his letters to Humboldt under this title, so it is a copy. And as regards Diophantus especially, Humboldt's request at the end of 1846 rekindled an eager interest in philological question on Jacobi's part. So, Jacobi in classical philology, it has become part of a well-known folklore that in addition to mathematics, Jacobi studied classical philology in Berlin under August Böck, one of the leading figure of classical philology in Germany at the time, took part in Böck's classical seminar there for some time, and caught Böck's attention by his outstanding intellectual skills. Okay, this folklore extending from Diriclet's eulogy, when at the death of Jacobi, Königsberger's Festschrift, to Erich Hecke's lecture notes on the history of mathematics here, as you see. Less well known, however, Jacobi's work on Diophantus deserves closer inspection and contextualization. So this is pointed out, of course, by Norbert in one of the paper that I mentioned in the beginning, but I would like to go into the detail of what Jacobi did actually, what kind of operation he performed, he carried out on the Diophantus text, or the manuscript that he could find. So all this deserves closer inspection and contextualization. During his stay in Rome between November 1843 and June 1844, Jacobi visited the Vatican Library and compared the Greek manuscripts of Diophantus preserved there. What kind of work was it? Which were the goals pursued? Which insights guided it as to the relation between ancient and modern mathematics? And this is really what is the main focus. And to what extent was it indebted to previous philological and historical work, in particular Nesselman's, but also Cobrooke's? Chasing manuscripts in Rome and Wolfenbüttel. Jacobi would later write to Minister Ladenburg. He had to justify himself writing an answer to Minister Ladenburg and explaining what he was doing. I am also occupied with the edition of the Greek mathematician Diophantus, for which I compared 6 manuscripts from the Vatican Library during my stay in Rome, and even now I still use a precious manuscript which I owe to the kindness of the Wolfenbüttel librarians. I hope to be able to complete this work soon and hand it over to the public. So this work was never published except for a short printed note. Jacobi's close acquaintance with Nesselman's book is probably not foreign to his decision to investigate into these manuscripts in 1883 and 1844. So now we have the benefit of the distance, of the historical distance. So we can try to understand what Jacobi was doing against the backdrop of current research, current knowledge, which is immensely increased in comparison with what it was in the 19th century. So here you see that Christianities and Hoax make a complete account of the story and the trajectories of the different manuscripts. So it turns out that Jacobi consulted and compared both these manuscripts, the Vatican, and also the Wolfenbüttel manuscript that is this one. Okay. So what I would like to clarify is the kind of work that was done, keeping in mind that one of the questions that were asked to him by Humboldt, concerned the relationship between ancient and modern methods. So what did he do? So comparing Diophantus manuscript, I put this under, I accompanied this with this well-known quote by Bertrand Russell, the method of postulating what we want has many advantages. They are the same as the advantages of theft over honest toil. But we will see here that postulation and honest philological toil are not so clearly separated. So they're intermixed in a certain way, and it's interesting to see how. So let's focus on this problem, to which Jacobi devoted some time and some of his energy. That is the 9 or 12, depending on the conspectus. It was in Bachet, it is problem 9 of the 5th book, Greek book of Diophantus, and in Tannery it is no, it's the reverse. Excuse me. It's problem 512, as here you see here 512, as Jacobi was referring to Bachet's edition. So, what is the problem? As a result of his perusal of some of the Vatican manuscript of Diophantus Arithmetica, Jacobi presented a paper at the Royal Prussian Academy of Sciences in Berlin in August 1847 under this title. The problem is this one. Okay, it's very simple. It's to find to divide the unit in two rational numbers, so that by adding a rational number to each of one, you obtain a square. You obtain two different squares. Okay, and this comes from the Conspectus of Christianities in Oaks. Jacobi begins with a very clear explanation of the prerequisite for launching into this enterprise. First, knowing that what the Greek called a diarismos is a necessary condition. The Greek, let's follow Jacobi for a while. The Greeks called diorismos, also prosdiorismos, the more precise determination of the given quantities, which is necessary to make the problem possible. These diarisms generally consist in the determination of the limits within which the given quantities must be contained, so that in geometrical problems the quantity to be constructed remains real, or in arithmetic problems the values of the sought numbers become positive. Diarisms referring solely to the form of the given numbers are sometimes necessary, as here for the solution to arithmetic problems, to be rational, or for the problem to be posed at all. So here, in the case at hand, the point is that you have an obvious necessary condition, is that by merely adding the two quantities, the quantity x plus a here and y plus a, you obtain this here. Okay, but this is of course not. This would be trivial. This is not the obvious condition that is supposedly Diophantus condition. So there is knowledge encapsulated in Diophantus diarism, and the whole point of all these people, Jacobi is drawing very much on the work of previous scholars, previous mathematicians, ever since Bachet to Nesselmann, is to try to recover or to regain this knowledge that is hidden, presumably hidden in Diophantus condition. For the problem at hand, this is still Jacobi writing. For the problem at hand, it would have been sufficient if Diophantus had observed as a diarism that the double of a given number increased by 1 must be the sum of two squares. This is the obvious condition. But this is not what he does. He does not explicitly state this condition. He presupposes it in his solution, and even that a decomposition into two squares is actually known. In contrast, Diophantus states as a diarism a property that a number which is the sum of two squares must possess. Diophantus diarism states nothing else than such a property, and he tries to figure out what it is. So in his view, the whole problem, I will skip, is that he tries to identify a property of sums of given number, but as Jacobi insists, he is careful not to state the converse. Whereas if you here consider immediately that it is the expected condition, namely Fermat's condition, then you would put the whole problem at a level and consider it in a way that you would immediately obtain the converse. So it is interesting to see this, so, that what Jacobi is after in all this note is to find a way to account for a non-trivial condition, okay, so that the statement and its converse here should not be put on the same footing. Okay? So which mathematics and how to read it in the Greek text to distinguish those different levels. So among the main issues laying in store for Jacobi are the following. What is the exact relationship between the sort property, here PB, and Fermat's theorem? Namely that an odd prime, obviously that an odd prime P can be expressed as sum of two squares if and only if you have this condition. Since the diarism is about rational, not merely whole squares, but mainly since Jacobi claims the converse as a special status. So we have to look carefully of what exactly is this distinction between the statement and its converse. And the other problem is that besides, in the Greek text, the necessary condition formulates in one single statement a double property in the form of a neither-nor alternative about the given number A. The given number A of the problem at hand. So let's see. Here, now in the current work, in the current scholarship, this problem is translated in this way. The text, the problematic Greek text is translated in this way. So the current, the options that are made now is to translate this proposition in this way. But Christianidis and Oakes explicitly says that they base themselves on Tannery edition of the Greek text, and Tannery is basing himself mainly on this manuscript in Madrid. So this is not the way that, this is not the context in which Jacobi worked, as we will see. He did not have access to this manuscript here. And here is the part of the diarism, the part of the problem. So You have the statement of the problem here, and here the diarism. That is the necessary condition. Okay? So the whole point is to arbitrate between, I mean, for those people in the 19th century who read Bachet's edition in including Fermat's observation on the text, is how to deal with the Greek text having in view Fermat's theorem. And it's not clear, against what may have been expected, it is Jacobi precisely restrained from simply imposing the Fermat's condition on the Greek text. And this is interesting to see how he did it. So here is the part that has to be considered. So this part is precisely problematic because in it there is a corrupted, it contains a corrupted part. So there is a range of variation. Okay, here if you compare Tannery and Bachet, and you see here, this is the corrupted part, and in both there is this habit of indicating the corrupted part between those signs. Stars here in Bachet, and here the same in Tannery. So this is the main thread of the story from the 17th century to the 19th century, dealing with the same problem, but making different choices. Okay, so you see here that the structure of the text, you see the alternative here, mete, mete. So the neither nor structure of the text. So this is the state of the art before Jacobi. Jacobi mainly drew on 3 books by Bachet, Schulz, and Nesselmann, these ones. And Schulz, Johann Otto Leopold Schulz, was a classicist and a gymnasium professor. Okay? So both Schulz and Nesselmann started with Bachet's text, struggling on the one hand to make mathematical sense of it. So what they had is precisely Bachet's text with Fermat, as you see here, Fermat observation. So trying to make mathematical sense of it, while on the other hand, closely pondering possible emendation of the text. And the point is that precisely Jacobi, whereas Jacobi in general is very much indebted to Nesselmann's scholarship on Diophantus, on this particular instance, he chose another path, or at least he ventured beyond what Nesselmann did, for good or bad reasons. We will see. So let's go back to Bachet's text, looking at it under the magnifying glass. All these people, Schulz, Nesselmann, and Jacobi, had to clarify a few spots in this part of the text. So here you see you have the neither nor clause. Between the 2 stars, it is the corrupted text, so we never know. It differs from one manuscript to another, so it's open to interpretation. And among those spots that require to be clarified in the first place, Schulz and Nesselmann highlighted the following ones. So this, how to read that? How is it? Should it be read as one thing, or one whole, or should it be divided in 2? So here, Schulz and Nesselmann propose to translate it by greater by 1 unit. This spot here, meros tetarton, the 4th part, and this spot here, measured by the prime number. So here are the choices that were made previously, before Jacobi. And if you recapitulate, you have greater by 1 unit, the 4th part, measured by the prime number. And as Nesselmann implied, all these parts of discourse presented themselves as scattered bits and pieces, not unrelated, not to say strongly evocative, of Fermat's vera limitatio, written as an observation added to Bachet's text. So they managed, Schulz and Nesselmann, to organize the text and to make translation decision, so as to make appear Fermat's vera limitatio. That is, Fermat's reading of what the condition, Diophantus' condition, should be. Although Nesselmann cautiously warned that there was a long way from the Greek text, however amended, to Fermat's condition. So Nesselmann is doing honest toil, okay? But still, he is very much, he has in view this well-known text, which was included in Bachet's edition. And instead of the dubious part in Bachet's text, Fermat supplied a necessary and sufficient condition for the problem at hand, called the Vera condition. And in short, it is this one, the expected one, okay? So having all this under the eyes, Schulz and Nesselmann and Jacobi had to arbitrate between mathematical and philological constraint in order to determine which condition was the more plausible. And these strategies were both suggested, but they had different strategies and based on different choices. So from the point of view of modern methods, Fermat's condition is a necessary and sufficient condition. Whereas Jacobi, on the contrary, aims at reconstructing the Greek text so as to identify a necessary condition here in such a way that the converse would not ensue from the presumably ancient methods employed, so that the diarism and the converse may not be on the same footing. What does it mean exactly? And this is really what Jacobi does, and it's very interesting to see. So to preserve a difference of level between one statement and its converse. So I will rush quickly into this. This is the layer of the land according to Nesselmann. Unfortunately, the diarism is badly distorted in the manuscript. And so, this is the interesting part. Bachet made guesses back and forth and occasionally got upon the track of truth. But since it did not know the position to which Diophantus referred, so since it did not know Fermat's vera limitatio, he neither succeeded in improving the text nor in giving the correct determination of the problem. Fermat did the latter without considering the text any further. Only Schulz has ventured to make this correction, but I think he has left something that is completely untenable. So here you see you have Bachet here who did not know the correct determination of the problem. Fermat did, of course, but did not consider this kind of problem. This was not his concern. And Schulz engaged into this back and forth work, but made a wrong attempt. So he avows he does his best, but he avows that one cannot make sense of the second half of the sentence here. So sieving difficulties out and forming Fermat's condition, and this is what here Schulz does, enforcing Fermat's condition, which Nesselmann refrained to do. He endorsed part of the modifications suggested by Schulz as the following, but never mind. He turned here. Never mind the kind of changes he made. What is interesting, what is important, is that, in short, Nesselmann claimed that a gap remained between Fermat's condition and the Greek text, and that the diarism hinged on the decomposition of this expression, okay, which we saw in the beginning. And he tentatively suggested that the whole diarism was about determining the form, this decomposition, okay? But here you had the mathematics on the one hand, very much based on Fermat's limitatio, and you had the text on the other hand. And Nesselmann pointed out that Diophantus knew that the product of two numbers of that are sums of two rational squares could also be written in this way. But he conceded not to be able to trace a path between the complete general decomposition while only using ancient methods. Okay, so this is the point. Having in view Fermat's condition, which gives the gist of the mathematics, but amending the Greek text while only using ancient methods. And he ends up with this wry note inviting others to do better, a call to the friends of conjecture. Okay? Apparently, Jacobi was not deterred from launching into this kind of endeavor, in spite of Nesselmann's irony, but in his view, there was more to it than a vain attempt. Jacobi's textual reconstruction was guided by a goal which he revealed only at the end of the paper, namely to mark the difference between ancient and modern methods. You know, recall that it is this question of making a difference between the statement, the methods required for proving the statement, and the methods required for proving the converse. So he wanted to account for the difference between both kinds of methods. Okay? In order to achieve this goal, he made a point to rise to the highest standards of the current philological practice, thoroughly justifying his choices by sophisticated arguments based on the largest number of relevant instances from the corpus. So mainly, he jettisoned some of the choices that were made by Schulz and Nesselmann, and instead, he enforced something which may appear as a drastic choice, that is, substituting here one proposition, upo, by another, para, hence devoting 3 pages long to proving that para in Greek text is also used as meaning subtraction elsewhere in Diophantus. And what is interesting is that incidentally, he deployed arguments that are confirmed by current scholarship. Okay, so this is why, you know, the demarcation line between a postulation and honest toil may be more mixed up than it appears. So let's go on. Jacobi then proposed the following emendation of the corrupted part of the Diophantus diorism. So what was the point of all this, besides displaying philological mastery? Jacobi's pivotal point is this one. On the basis of this textual reconstruction, Jacobi chiseled a framework consisting of 4 propositions in order to prove the diorism formulated in the terms above, using tools and methods allegedly available to Diophantus, as testified by the extant text, but more importantly, and this is the main thing, he did it in ways that supposedly made it clear that Diophantus' methods provided tools for proving the diorism, but not its converse. So in other terms, you see, the whole point was to make a difference between one sense and the other. So Jacobi's argument is in 3 steps, and it's useful to rush through it. So he has also, like the previous authors, Fermat before his eyes, but he made clear that his reconstruction of the text maintained this difference between these 2 levels. Okay? And this is the conclusion. No matter Jacobi's conclusion in this paper, and which is important for what comes next, no matter how many different ways have been used since Euler to prove it, there is no analogy in the mathematics of the ancient world for the methods required. So there is no analogy here. Even though, of course, Diophantus will always was considered as giving the first impulse for further work in the 17th century, as is well known. But he insisted on this. There is no analogy. So let's go back to Jacobi's correspondence with Humboldt and how on the debate which comes later after his paper on problem 512, and let's see how Humboldt's questions revived or rekindled his former engagement. Jacobi's pithy assessments of the Diophantus method. Here, you see, his main point is about the fact that in in Diophantus you have only one variable. Jacobi insisted on the fact that it was turning a defective symbolism into a strength. Diophantus shows in particular his skill in the solution of the equation in which he at once so perceived that he only needs one unknown quantity, but this acumen appears as a product of necessity because of a defective symbolism. And here, you see, I don't have time to go into this, but it would be interesting to unfold what he is obviously referring to Colebrook's a new scholarship, making that clear in his translation of Bhaskara and Brahmagupta. Second point is about another way to an interpretation of the procedure aoristos to solve a problem in an indeterminate way, which is also a way to compensate for the fact that you only have one variable. And here, Jacobi is very much indebted to Nesselmann, so it could be shown in detail. But I rush to the main part. And Jacobi writes, the greatness of Diophantus consists in two things. He knows how to introduce, owing to general substitutions, such new unknowns that one can rationally express the old ones by means of these new ones, in which his methods still find today important application in the integral calculus where such transformations matter. So here, in commenting this part, Joseph Hoffmann referred to the 1835 note we started with. But you see here, he never considers that, he never ignores the difference in character between the ancient method and modern methods. And the second point is about the bounds. The way in which Diophantus stands out is the fact that he knows how to determine in very complicated expression the bounds within which one has to assume the value of the unknown, so that one can have, so that the value of the old sort unknowns of the problem become positive. And so here, this problem, which is the problem of the bounds, Gensen, is central in Nesselmann's account of Diophantus' method. So here, on both ways, insisting on substitutions and diarisms, he is very much indebted to Nesselmann. So in conclusion, one word of conclusion, an ampliative view of mathematics. Remember that in the 1835 note on Diophantine analysis, Jacobi spoke of Abel's theorem as mira illa theorematis Euleriani amplificatio. One may call ampliative the process by which Euler's theorem came to be successfully extended into Abel's theorem, a much more general and much deeper theorem. In their report on Briel and Noether, devoted a whole section to tentatively reconstructing what this process may have been, striving to bridge the gap between Euler's and Abel's theorem. One may argue that Jacobi held an ampliative view of mathematics, which also shaped the way he considered history of mathematics. And here you see, I don't have time to read those quotes, but he maintains this view that you have Diophantus' method, which, unlike Nesselmann, he considered that do not pertain to algebra proper, and then Eulerian and post-Eulerian methods in Diophantine analysis relate in the way Jacobi conceived in general the relationship between algebra and analysis in general. So here, you see, he gives no more than a few suggestive hints in this respect. And in the case of Diophantus and Diophantine analysis, Jacobi's ampliative view of mathematics and history amounted to considering that Diophantus' method have a distinctive character, setting them apart from modern method. That was the whole point of his note, 1835 note, a distinctive character which can only be established owing to philological methods, no less than algebraic methods are distinct from analytical ones, but at the same time that Diophantus' problem occasioned and gave the impetus for new theories. As Euler's theorem gave rise to Abel's theorem, which in return constitutes a wonderful amplification of Euler's theorem. So you have this idea upon which Jacobis insist that with this ampliative view of history of mathematics, you may have, and you obviously have, analogy in the statements, but if it is an ampliative process, you don't have analogy in the methods themselves used to prove this theorem. And so this is it. Thank you very much.